So in this lecture, I'm going to discuss fluid pressure and fluid force, and actually force is what we're after primarily. And so this is the idea of, for instance, is how much water can a dam withstand, that we need to make the dam strong enough, for instance, to be able to hold back the force of the water that's behind the dam, or how strong we need to make a window on a ship that is below the surface of the water to make sure that that doesn't burst, the strength that the force that that window needs to withstand, and so on. We start out with the idea of fluid pressure. Fluid pressure is a force per unit of surface area. So when we think of something that is actually underwater, now the fluid doesn't have to be water, it can be any liquid, or actually a gas could be thought of as fluid. But if we're thinking of something underwater, we can almost think of, well, the pressure, how much weight is the column of water that is above that object? That would be kind of the idea of the weight that is on that, or the pressure that is on that, because we do it per unit of surface area, like I said. Anyway, here's the way we start with this. Fluid pressure is equal to weight density. Well, that's the weight per some volume. Weight density times the depth. That's what we'll work from. And we'll call fluid pressure P for pressure, of course. Weight density, we're going to call W for weight. And H we'll call the depth. Now, based on this, fluid force, which we're mostly interested in, fluid force is the fluid pressure times the surface area of the object we're measuring the force on. Well, so in that terminology, the force is equal to the fluid pressure times the surface area. And since the fluid pressure is the weight density times the depth, then the fluid force is nothing more than WH times A. That is density times depth times area. That's what that boils down to. Density times depth times area. So let's look at our first example. And the first example is a very basic type. It will get more complicated when we change the situation. Find the fluid force let me get this written down. Okay. As I was saying, find the fluid force on a rectangular sheet of metal measuring, see, I didn't spell that correctly. I'm sorry. Measuring 3 feet by 4 feet, and this sheet of metal is submerged in a horizontal manner in 6 feet of water. Now, the significance of a horizontal manner is that the entire surface area of this sheet of metal is all at the same depth. You can imagine, so if we have it horizontal, and I'll try to make it look like this is horizontal, and it's 6 feet underwater, and we'll say this is where the water level is, and then it's 6 feet to any place on that sheet of metal. So the depth is not changing, and that's pretty critical here. So anyway, how do we measure fluid force? Well, fluid force is, F for fluid force, is density times depth, once again, times surface area. Well, or as we said, W times H times A. Well, we have to kind of remember from things that we've already done, but the density, which is more or less a weight of water, and in this case we're assuming fresh water, density of fresh water is 62.4 pounds per cubic foot. So our force is 62.4 pounds per cubic foot times the depth, which is 6 feet, times the surface area. Well, the surface area of this is 3 feet by 4 feet, so the surface area is 12 feet square feet. And so as we work through this and do the calculations, it's simply going to be 4,492.8 pounds of force. You see our feet all, whoops, that was feet cubed here, pardon me. Our feet all cancel, so we're left with only pounds. And of course, we're measuring force in pounds, just like we have done previously. So this is a simple type of problem, and I say simple because the object that the force is on is, the pressure is the same all over the object because the object is at the same depth for its entire surface. So that's what makes this simple. On the next page, we'll change this. We'll actually have a vertical plate, and the problem with a vertical plate is we have different depths. We have, if you will, an infinite number of depths all along that vertical surface. So that makes us do things a little differently, and that's why we have to use calculus. Okay, I've began setting up a discussion before we actually do a problem. And now we're talking about force on a vertical plate, that is something that is submerged under water or under a fluid in a vertical nature rather than a horizontal nature. And the issue here is that, remember, force has to do with depth. And this one particular object, the parts of this object are at different depths. So the top of the object is at a lesser depth than the bottom of the object or the middle of the object. And so we have to use calculus because we're having the depth being a variable here. And that's the whole issue. Now, there's two ways to set up a problem of this nature, and it has to do with how we set up and discuss depth, more or less. So what I'm going to do over here to the left is I'm going to give this idea first. Is we think, of course, our y-axis as being in a vertical nature, that's along the y's, and in this case, I'm thinking of the fluid level, where we are, the fluid level being along what we would think of as the x-axis. So now, in that case, we have some value. Let's just look at it this way. We have, we'll say that this value down here at the bottom of this vertical plate, we'll call that value C. Of course, that's a negative number because it's below the x-axis. And we'll have this value right here where the top of the plate is, we'll call that D, and that also is a negative value because it's below the x-axis. Now, here's our situation. since we are at variable depths, we pick a particular y level. So, one particular level of y. This is the y level we're talking about. And we think of a strip of this plate that is infinitely thin, running along the length of that plate that is underwater. This is infinitely thin. Well, the height of this plate, the measurement, the vertical measurement, since it's infinitely small and it's a vertical measurement, I'm calling that dy. Now, it depends on how wide this piece is. It's not always going to be something that's rectangular here, but we're going to call this length in this case. We're going to need to get that done in terms of y. So I'm calling it L for length, and that needs to be a function of y. In other words, it needs to be y stuff, the way we describe that, although it is horizontal, and that's the way we measure x's. And look, this particular strip then, remember this strip could be at the top, could be at the bottom, could be in the middle. In fact, we're going to have that strip all the way through this. But for this particular strip, or slice, as I've called these things before, it has a measurement, its depth, okay, has a measurement that I think we call the depth h, so we'll call this h of y. That's the depth of that particular slice or strip. And it needs to be as a function of y also. Okay? So under these circumstances, let's just look at these particular circumstances, then if we can come up with those functions, then the force that is on that particular slice or strip, okay, is going to be the density of the fluid, that has to do with the type of fluid, of course, times the depth times the surface area of that strip. That is, density will be something that's given to us. Well, if it's water, it's fresh water, 62.4 pounds per cubic feet, and so on. If it's salt water, then it's 64 pounds per cubic foot, and so on. We'll be given that information. Now, the depth at this particular strip is h of y, and the surface area in this case would be the length of that strip times the height of the strip. So that's the surface area. This is the area, this is the depth, this is the density. So that's the force on that one strip. Now, the total force on the entire plate then would be adding up the force, all of the forces applied to any strip that we could have, starting down there at the bottom and going all the way up to the top. And there's an infinite number of those, and so we use integration to add up the infinite number of those strips. That is the force on the infinite number of those strips. So the total force comes about by using an integral. The force is equal to the integral starting at the lowest place that strip could be and going to the top place that strip could be. So from C to D of W h of y times L of y dy. Now, of course, the W is going to be just a constant. And so we would have force, in this case, is equal to the density times the integral from C to D of h of y, L of y, dy. Now, I don't propose that you memorize this formula. What I propose we do is understand how we thought about that. Now, we're going to look at another way to set a problem of this nature up, and just so that we know what we're doing. It's going to look similar, except that our limits of integration are going to be different. So let me pause for a moment as I draw another diagram. as I was drawing this diagram, it occurred to me that I failed to mention something pretty important in the above diagram, in the orientation that we have it set up above. So we'll temporarily look at the top diagram again. Now, remember, we talked about h of y being the depth up above, right here, h of y. Notice that what we're doing is what I said over here on the left, that strip is at the level y. Now, in this case, remember, that represents a depth. And so we can see, oh, the top of the water line is being up here, or the fluid line, and we're down here at the y level, but that y is actually, see, this is the depth right here. Okay, this distance is the depth. But that y is a negative number. So in this specific case, this h of y is really the opposite of what y is. For instance, if y was a negative 5, well, then the depth, we don't say it's negative 5 feet, we'd say the depth is 5 feet, the negative of negative 5. So in this particular case, we would actually have this h of y being simply negative y. Okay, recognizing that that represents the depth if we're at the y level underwater. Okay, now in the bottom, let's look down here at the bottom. In the bottom example, notice where I put the x-axis. I put the x-axis actually at the bottom of the plate instead of at the water level. So in the orientation, all of the y's we're dealing with are positive numbers. In the orientation above, all the y's were negative numbers. So as we come through and think of the force in this case, then rather than going through all of those examples again, we'd have the total force, going through the slice business, the total force once again is going to be an integral. But here's the issue this time. In the case that we see is if the bottom of this plate is at the x-axis, then we're going to start those values at y's that are 0, those strips at y that is at 0. And it depends, of course, on how tall this object is, but we'll say that this value is A. Okay, so this position is A, and so we would integrate from 0 to A. We'll have to figure out what that position is. It would be how tall this vertical plate is. Okay, so we'd integrate from 0 to A, the density times the height function times the length function dy. Okay, so we're really, what is that? That's the density times the depth times the surface area. Now, the problem now is with this depth function. The length function we're going to have to figure out, but the depth function is the issue to worry about now. And so what you see, what you see is that it depends on how far underwater we are. And that might have to do with, we'll kind of determine, the water level based on where the bottom of this vertical plate is. We'll call that water level at B. So the issue now is the depth. The y that we're at is right here. Okay, this is where the strip is. That's a particular y value. And we're letting those y values go from down here, which is where y is 0, to up here, which is where y is A. But this particular strip is at a depth. It's this depth. And that depth is all of B subtracted away from y. The entire, from the bottom to the top to the water level is B. but it's not that far because we're y units up. So this distance that we're talking about here, this height, that's the height, is b minus y. We would have to figure it in that way. So in this particular case, as opposed to the above part, this height function would be this b minus y that we'll have to calculate. And then we would be able to continue the problem. Okay, well, we're going to, on the next page, look at an actual example, and I think that I'll do the same problem two different ways, depending on how we set up the problem itself. Okay, our problem here is that we need to calculate a force. As you see, we have a dam that's shaped, or you don't see, but you read. We have a dam that's shaped like a trapezoid with a height of 60 feet. The width of the top of the dam is 100 feet, and the width at the bottom of the dam is 40 feet. Find the hydrostatic force that the dam will need to withstand. Now, when we talk about what will it need to withstand, we're going to assume it would need to withstand a water level that is to the very top. Of course, there's usually a spillway for most dam situations where it goes around the dam if it gets too full and doesn't actually go over the top. But we're going to assume what we need for the dam to withstand in case it actually gets to the very top of the dam. So let me first draw a diagram the way I'm thinking of this the first time around, and then we'll look at a second opportunity, a second thing we could do. Well, now I'm kind of embarrassed of this diagram I've drawn, but please believe that that's supposed to look symmetric. So here's what I've done. You can see the trapezoid that represents the dam, and what I'm imagining is the bottom of the dam. Actually, this is not what I wanted to do first, but that's what I've drawn. The bottom of the dam is sitting on top of the x-axis, and so the top of the dam would be where the maximum water level would be. Okay, so we're thinking about the water being up here. Now, because of the way we've drawn this, we know a couple of things. So let me point out that we know that the entire width of the dam is 100 feet. And so over here to the right of the x-axis, the distance along here is 50 feet. And at the bottom, the entire width of the bottom of the dam is 40 feet. So we know along here is 20 feet. Okay, we know that, what else do we know? Oh, we know that the dam itself is 60 feet tall, so this distance is 60 feet right there. Okay, now what we're going to end up doing, here is that we know kind of how to set this up. We have some idea, and what we're going to end up needing to calculate is the amount of pressure on a strip of this dam that's infinitely small. And just as before, this would be a dy. Now, here's the issue that we've got this time. Of course, this strip is not going to be the same width every place on the dam. So we don't have a constant here. This length that we're needing to calculate surface area with, length times height here, length times width, this is going to be different depending on where we are. So that's the reason that I said it with a variable y. As we move up and down along that dam, then that L of y, that length is going to be different. Now, what we're going to do, and that's this whole distance across here, okay? So let's at least write down, though, what we're going to do. For this particular strip, the force for this strip or this slice will be the weight density times the depth, we'll have to talk about here in a moment, the height, times the surface area on the strip of the strip. And so we're going to have to come up with what this function is and what this function is before we can integrate, because the hydrostatic force is going to be the integral of W times H of Y times L of Y times dy. Now, how are we going to integrate? Well, notice that we're starting those strips at a Y value of 0, because remember, the bottom of the dam is on the x-axis, and that's where Y is 0. And we're going to move those strips all the way to the top of the dam, but the top of the dam is 60 feet higher. So in this case, we're going to integrate from 0 to 60. Okay. But now we've got our work cut out for us. Okay. And so I guess let's first think about this height, because this is the distance that we're talking about for height. Okay. Or depth, pardon me, depth. But we're calling it H of Y. So that particular value, now remember, we're at a given Y value that's changing. See, that Y value is going from 0 to 60. That strip is going from 0 to 60, and that's a Y value. So when we're at that particular Y value, what depth is that? Well, it's not Y. Okay, it's not Y because that's how far we are from the bottom. So the height function in this case is actually 60 minus Y, all the way to the top, but subtract how far we are from the bottom, and that's actually the depth of the water, okay? The depth that that strip is from the top, from the water level. I hope that makes sense. So we've got the function H. Now, the function L is a little bit more involved. So let's come over here and let's talk about this L. And what I would like to see, the problem is this L is defined by these two sides, isn't it? It's defined by this and, of course, over here. But because of the symmetry, what I would like to do is calculate this particular distance right here. Okay, just this side. And notice, though, if I call that my x value that I'm needing to calculate, okay, if I call that my x value, then the L of y is going to be 2x. See, I've got that much on the right and that much on the left of that y-axis. So L of y is equal to 2x. I just need to figure out x. But x depends on this edge, okay? And we can think of that as a line on a coordinate axis. And we happen to know 2 points that are on that line. See, let's look up here at the very top. We know from the y-axis to that outer edge at the top is 50 feet. And we know that top is 60 feet from the bottom. So this point is actually the point has an x value of 50 and a y value of 60. And when we look at this bottom position, well, of course, that's at the y level of 0. And so that point, of course, is 20 feet from that y-axis. So it has an x value of 20 and a y value of 0 in this case. Now, that really tells us that we know 2 points that are on that line. And so we ought to be able to calculate the equation of that line. And to calculate the equation of the line, okay, here's what we know. In general, the equation of the line we see is going to be of the form y is equal to 2x plus b. Pardon me, mx plus b, slope, I'm sorry. Now, in this case, the b is not so clear, okay? The b is not so clear because we don't really see where it's going to cross the y-axis. But since we have 2 points that are on that line, we can figure it out. In fact, we're going to use those 2 points to calculate the slope. And to calculate the slope, we use the slope formula, which says, okay, we know 2 points. We take the y value of 1 point and subtract the y value of the other and divide it by the x value of that point again and subtract by the x value of the other. In other words, the y sub 2 minus y sub 1 basically is the rise, and the x sub 2 minus x sub 1 is the run. And so I'm going to use the top point as y sub 2. As point 2, if you will. So the y sub 2 would be 60, and the y sub 1 would be 0. And we're going to divide that by the x value of the top point, 50, minus the x value of the bottom point, 20. And when all's said and done, that's 60 over 30, or 2. Kind of got ahead of myself a while ago. Well, again, we could just look at it as rise over run. We're doing what? We're rising 60 feet, and our run is 30 feet. Okay? Anyway, we have the slope. Now that we have that information, okay, let's kind of keep over here while we're doing this work. Now that we have that information, we know the equation of this line looks like y is equal to 2x plus b. But we still don't know b, but we can use either of the points, along with the fact that we know this point 20, 0 is on the line. So that means if we use an x value of 20 and a y value of 0, the equation has to be true. So we'd have a 0 for y and a 20 for x. And if that equation has to be true, then we can determine that b itself, in this case, has to be negative 40. We're just solving for b. So in this case, we have b itself as negative 40. Now we know that the equation of this line is y is equal to 2x minus 40. Well, so what good is that? Well, remember, way up here, we wanted to know the half the width of the whole length of the strips. And we wanted to know x right there. We wanted to know that x. And to know that x, we need to know, because that x depends on the line. See, the x value is the measurement to that line. And this gives us the relationship between where we are, the y value we're at, and the x value that we have. And so what we end up doing is solving this basically for x. Okay, so to solve this for x, we would add 40 to both sides, and then we would divide both sides by 2. And so we would have x is equal to y over 2 plus 20. Oh, but remember, back up here, we said the length, let's see, we need twice of that x, don't we? So now we have a way to calculate the length function. So we already had, let's kind of recall back here, we have the height function, or the depth function is 60 minus y. And now we're going to calculate the length function so that we can calculate that surface area. The length function is 2 times x, and our x value is y over 2 plus 40, which ends, plus 20, pardon me, plus 20. And so our L function is y plus 40. That's that length, y plus 40. So now that we have that, we can set up our force integral completely. Remember, force is what we're calculating, and we already decided we're going to integrate from 0 to 60, and we're assuming fresh water. Okay? We're assuming fresh water. Where else do we have a dam? And if we're assuming fresh water, then the density, okay, the density, which is well, I'm having all kinds of problems spelling. The density of fresh water is 62.4 pounds per cubic foot. And that's the W value. Okay, so we have our W value, density 62.4. Our depth function which is 60 minus y, times our length function, which is y plus 40 dy. Now remember, this is the density, this is the depth, okay? It's what we call h of y, and all of this together here is the surface area of that strip. Length times height in this case. Well, I don't want to, how would we calculate this? Well, what we would end up doing, of course, is having to multiply that 60 minus y times that y plus 40. And I'm not going to go through all of that, but of course we could actually factor that 62.4 out. So we're integrating from 0 to 60. And let's see what we would get when we multiply those two binomials together. This is a dy over here. So I believe we would get 2400 plus 40y, oh, not 40y, 20y, 20y minus y squared. So that's what we would integrate and then evaluate from 0 to 60. And when we do that, you can like I said, after the calculations, we get 6,739,200 pounds of force. I'll let you actually do the integration, but that's what I got when I did it. And you can certainly do that integration without much difficulty. Okay, that's one way to set up the problem. On the next page, I'm going to set up the problem a little differently, and that is I'm going to have the x-axis at the top of the dam. And you'll see that we'll go through the same process. We'll think the same way, but the way we set it up and what we actually integrate, our integrand, and our limits of integration will be different, but we'll get the same answer. So we'll pause as I set this up. Okay, we've got the same dam that is 60 feet tall. Now what I've done here is that I've made the top of the dam the x level. So that would be like where the water is. Maybe this is a little more natural. And if the dam is 60 feet from top to bottom, then this y level right down here would actually be a negative 60, wouldn't it? This entire distance would be the 60 feet. But that's a y level of negative 60. Now, in this case, when we create a strip along here, when we create the strip, then we more or less have the same scenario that we had a while ago. Oh, by the way, of course, it's across the top, it is a total of 100 feet. So this half on the right side of the y-axis is 50 feet. And likewise down here, the bottom all the way across is 40 feet. So we've seen this idea, that is the 20 feet there. And we may need to know these 2 points again. So let's think about what these two positions are. Remember, at the top, we're at the x-axis. And so that's actually, that's a y value of 0 again, isn't it? But it's the x value of 50 and a y value of 0. And down here at the bottom, then this is an x value of 20, but a y value of negative 60. Okay, keeping in mind those 2 points, because we're going to have to calculate the equation down the line again. Now, we're interested in this entire length. That's what we call our L of y. And we're interested in the depth, okay? And that's from here to that strip, and that's what we call our h of y. So we know that we'll need those. There's our L of y, and this is our h of y vertically. We know we're going to need those. But as we did in the last example, we're going to call half of that L of y, that's x. That's the and that makes sense. That's a horizontal measurement from the y-axis over to this this edge of that strip. Now we're assuming this is at the y level. Okay, so this is now y level is moving down from a -60 all the way up. See that y is going to be moving. That's what's going to happen. It's going to move from the very bottom to the very top. That y level represents a particular depth. So in this case, okay, we've got to remember what this y, let's look up here, this h of y, that's the depth. Well, it's down at the y level this time. See, because the top is at 0 feet. So the depth is at the y level, but y, since it's below the x-axis, is a negative number. So to talk about the depth, we need to say negative y. Now, in this case, to calculate the L of y, once again, we need to know that that's going to be twice what x is. And to finish that out, we need to know what x is by determining the relationship between y and x. In other words, determining the equation of that line that defines the right side of the stem. And so we're back to this idea that y is equal to mx plus b would be the equation of that line. Now, in this case, we could calculate the parts, but, well, let's go ahead and let's go through it just like we did before. We need to calculate the slope. And in this case, the slope would be 0 subtract -60. That's the difference of the two y values, divided by 50 subtract 20. That's the difference of the two x values. And we'll get 60 over 30 again, which is 2. Well, that's no surprise. Now, we use that information along with the fact that we know the equation will look like this, and we can use either one of those 2 points to finish this out to figure what b is. If we use the fact that we know the point 50, 0 is on the line, that means if y is 0 and x is 50, we have to have a true statement. And so that allows us to calculate b. In this case, we would get b is equal to -100. And so now the equation of this line, because it's a little different orientation, is y is equal to 2x minus 100. Now, notice something, this is kind of, this wouldn't always work. Remember last time what I did here is I solved for x because x is what we need. But the length function, that is the entire width of that strip, L of y, is 2 times x. And if we notice here, there's 2 times x right there. So we could actually just solve this for 2 times x. That is, we could add 100 to both sides, and that's actually 2x. And so that's kind of a fortunate situation, is what y plus 100. And remember, we need this in terms of y. That's the reason we're doing this, because we're going to have an integration in terms of y. Because the width we have right here, this width for that surface area is dy. Okay, so here we go. The force on the dam that the water would create on the dam if the water was to the top level is going to be an integral, because we're adding up the force on forces on one particular strip. Okay, so and this time we're integrating from a lowest y value of -60 to a highest y value of 0. And we're still going to have the density of the water, which is 62.4 that we'll fill in, and the depth, okay, which we have a value of, which is -y, and the surface area, which is the L of y times dy. That's the length times the height of that strip. Well, as we fill these pieces in, of course, then, we'll have a integral from -60 to 0 of 62.4 pounds per cubic foot times our depth figure, our height, our depth function, which is -y, times y plus 100 times dy. And so as we factor out that that 62.4, we'll have an integral from negative 60 to 0 of negative y squared minus 100y. And you can see that this is a little simpler in the way that we'll have our integrand. And you know, it's not that big a deal, but it's a little simpler. And when we calculate this, if you go through the process, of course, you'll get exactly the same answer. 6,739,200 pounds of force that dam is going to need to be able to withstand if the water level gets to the top. Okay, well, I hope that was useful to see it set up in a couple of different ways. And of course, you pick the way that is most comfortable to you as you work through problems of this type. But they give you some options. Well, next we're going to look at a little different twist where we maybe have a different type of surface that is having force applied to it. And we'll do that on the next page. As you can see, our next example is about a circular window on a ship. We have a circular observation window on a marine science ship. It has a radius of 2 feet, and the center of the window is 8 feet below water level. What is the fluid force on the window? Well, this problem has several issues that we're going to have to deal with. And the first is that we're not in fresh water. Marine, of course, implies ocean water or water with salinity, salt water. So that's one of the things that we need to know here is the density of salt water. You need to be careful of this in the future. You need to be have a way to look up densities of fluids, or hopefully the problem itself will tell you. Density of salt water is 64 pounds per cubic foot, rather than the 62.4 pounds for freshwater. Okay, now the next issue is how we set up the problem, the little diagram we use to set up the problem. And it's very natural, but I'm going to tell you in advance this probably isn't going to be very useful or helpful. It's very natural to set up a situation where we have a y-axis and we have the x-axis that's actually at the water level, okay? Because we're thinking of the observation window of being underwater. So this isn't going to be the scale. Let's suppose this is where that center of that observation window is. Okay, so we've got a observation window. Now this level, of course, is 8. It says the center is 8 feet underwater. So if that's the x-axis up here, this value would be -8, and this value would be -6. Whoops, this value would be -6, and this value, of course, would be -10. Well, what we're going to end up doing, let me just kind of remind you, is somewhere along the way, we're going to be cutting this into a slice, like into little tiny slices. So far, so good. This looks like what we've normally done or we did in the past. And this dimension of that slice is dy. And we're at some y level, okay? So this slice is at some level y. Now, when we start deciding, and the symmetry here again, remember the length we're interested in, okay? The length we're interested in is this length right there. We call that L of y. And let's just come over here and kind of keep track of things. The depth for this slice, the depth of the slice, so that right now I'm just worrying about that one piece. The depth of the slice, well, it's going to be, now remember we're at the y level, but y is below the x-axis. And so the depth, which we called h of y previously, is the opposite of the y value that we're at. And the area, the surface area of the slice, of that slice, we called L of Y, excuse me, we didn't call L of Y. We said it was going to be the length of that slice times its height, okay, or width. So we need to know the length of that entire slice. Now what we've done in the past is that we said, let's take half of that slice. So 2x is that full length. We call that half of that slice x. 2x is that full length. Well, what we need to know is an x value for a position that is on the circle. That's a positive x value. So what we need next, okay, so let's get back to what we have up here. The surface area is actually going to be our L of y, which is 2x, when we figure out what x is, dy. Okay. And so, once again, let's, before I go too far, let's look at what this force for that slice, okay, the force on that particular slice. Well, the force on the slice would be negative y, excuse me, our density, 64, times our depth, negative y, times our surface area of the slice. The problem is we need to change this 2x stuff into y stuff so that we'll be able to integrate in a moment. And so that's back to where I was saying a moment ago, is that we need to find the relationship between x and y at this point. That point is on the circle. So we need the equation of the circle. That's the next thing we need to worry about, the equation of the circle. Well, generally, the equation of a circle is x minus h, that's not the h that we're talking about here, squared, plus y minus k, the quantity squared, is equal to the radius squared, where hk is the center. So in this case, and the radius, of course, in this case is 2. Well, in this case, the center, let's see, we have an x value of 0, but a y value of negative 8, don't we? So as we calculate this, we would get x minus 0 squared, so that's x squared, plus y minus our k is negative 8, so that would be y plus 8, the quantity squared, is equal to our radius squared, and our radius is 2. 2 squared is 4. So here we have an equation that has x in it, and so we can get the value of x that we were looking for above in terms of y. That is, first off, we would have x squared is equal to 4 minus y plus 8, the quantity squared. Now, in this case, the x we're talking about is on the right side of the y-axis. So that part of the circle, on the right side of the y-axis. For all of those x's, we actually have positive x's. So we would say that x, instead of saying plus or minus the square root, in this case, we know the x is positive. So we would say just simply the positive square root of y plus 8, the quantity squared. Now here ends up being the problem then. For us to calculate the total force, remember that was the force up here of just that slice or that strip. The total force that we would have, okay, in general, if we were calculating this, would be an integral. We're going to start these slices at a y value of negative 10. And we're going to stop these slices at a y value of negative 6. Now what are we integrating? Well, we're integrating the force for that's a single slice. Remember, in this integration adds up all of those forces. So that's for a single slice, we have 64 times negative y from above times 2 times x. Well, the 2 times x. The x is the square root of 4 minus y plus 8, the quantity squared, and then, of course, dy. And we could simplify this sum, and we could do a couple of things. I see that we have a negative in front of the y, so we could kind of think of that as a negative 64y, and that too, the negative 128y. So we could actually factor out this constant of a negative 128, then we'd have the integral from negative 10 to negative 6 of y times the square root of 4 minus y plus 8, the quantity squared dy. And if we could evaluate that, we would be in good shape. But this itself is a little bit of trouble, actually doing this. I suppose we might be able to use some other technique that we haven't been introduced to. And I suppose we could use a tool like Maple. But what I'd like to do is pursue the idea of what would happen if we set up our diagram a little differently. That is, rather than centering the window underwater, putting the center of the water at negative 8, why don't we put the center of the window actually at the origin, and we would have a simpler equation for that circle. Let's see where that takes us. We'll start that on the next page. Kind of set up our observation window so that the center is at the origin. So the water level then is 8 feet above that. So you can see I've indicated the water is up here where y is equal to 8. So on this scale, or on this axis, then the top of the observation window is at 2, and the bottom of the observation window is at negative 2. Of course, those are y values. The density of the water, of course, is still 64 pounds per cubic foot because this is salt water. Now, the way we would measure depth, okay, and remember we've called in the past this depth function h of y. And that's probably a habit from an old book. Anyway, the depth, at first it seems unnatural, but it's actually the distance to the top of that where the water is. So it's the distance from the top subtract the level that we're at, and we're at a y level. So just imagine if we were looking at this strip. Now I'm talking about the depth of a slice, okay, the slice that we're looking at. My apologies there. Okay, well, the depth of a particular slice, and it depends on where that slice is. When that slice is at a y value, then the depth is 8 minus y. For instance, if we were at the y value of negative 1, well, we would have all of that 8 feet above it, but we would also have the 1 foot below the x-axis. 8 minus negative 1 is 9 feet, and that's exactly where we were. Or if we were at the y value of 1, then we would be at 8 minus 1, or 7 feet underwater. Okay, so, at the very bottom of the observation window where y is negative 2, that's 10 feet below the water. Well, that's 8 subtract negative 2. So it does make sense to say that this depth is 8 minus y. Okay, now, the length function, okay, and once again, pardon me, this is the length. Okay, right here's the length. And that's what we call L of y. Now, the length of the strip. See, because we have the area of the strip, of that strip is going to be the length of the strip times the height of that strip dy. That's how we're going to calculate that area. But the problem becomes this ly. Well, like we've done before, we're actually going to look at half of that strip. We're going to look at that half, and I made it too small. We want to know what this distance right here is, and that's an x value. And so we're going to take that x value and we're going to double it. That is, L of y is actually going to be 2 times the x value that we're calculating. That x is the distance from the y-axis to the circle. And of course that changes where we are on our strip. So we'll figure out what 2x is, and then we'll have the length of our strip. Now, to do that, we've got to know where we are on the circle again. So we needed the equation of the circle, but this time the equation of the circle is much simpler, okay? The equation of the, and that's how we're going to find x. The equation of the circle in this case is x minus 0, because we're at the origin, squared, plus y minus 0, because we're at the origin, squared, is equal to 2 squared, or 4. So the equation of the circle is much simpler, and likewise we would solve for x squared first, so we'd have x squared is equal to 4 minus y squared, but our x is positive, and so we can say x is the positive square root of 4 minus y squared. Okay, so then our 2x, see, when we take this x and we double it, then we'll be able to calculate the surface area. So here we go again. Let's write this out. The force on the slice or the strip. Remember, it's density times depth times surface area. And we have all of those components above. The density is 64. The depth is 8 minus y. And the surface area is 2x times dy. Well, 2x, we need to write in terms 2x is the same as 2 times the square root of 4 minus y squared dy. So to find the total force, we're going to integrate. Now our strips this time are starting at -2. That's the lowest y value, and they're stopping at +2, the highest y value on that observation window. And we're integrating, of course, 64 times 8 minus y times 2 times the square root of 4 minus y squared with respect to y. Now, of course, we can simplify that a bit. We can certainly factor out, in this case, a 2 times the 64, can't we? So we'll factor out 2 times 64, so we have 128 times the integral from -2 to 2 of 8 minus y times the square root of 4 minus y squared with respect to y. Well, this integral is also a little bit troublesome, but I'd like us to plow ahead, and I'd like you to recognize that we could multiply this square root times the 8 minus y. So we'd have 8 times the square root and a negative y times the square root. And so we could actually break this into 2 integrals. So let me write this down here. Well, I have 128 times. Now, the first integral will be the integral from -2 to 2 of 8 times the square root of 4 minus y squared. I'm really leaving out a step, because first I would do the distribution of that square root, and I'd see that I'd have 8 times square root minus y times square root. And it's that I'm breaking apart into 2 integrals. So I'll say minus the integral from -2 to 2 of y times the square root of 4 minus y squared. Now let me tell you why I've done this. When I look at this second integral, then substitution will work very nicely here. And if I had some space on the side, I would do it in that fashion. So what I'm going to do right now is I'm going to take that second integral. We'll come back to this messy business that we've got. Now I'm going to take that second integral, which is the integral from -2 to 2 of y times the square root of 4 minus y squared dy. Now, if I let u be what is underneath the radical, 4 minus y squared, then this lends itself very nicely to this substitution, because du will be negative 2y, won't it? dy. So du will be negative 2y dy. So what I can do then, of course, is I can manufacture my negative 2y dy by saying, okay, I'm going to put a negative 1/2 here in front of the integral, and I'm going to put a negative 2 in front of the y, and now I have it set up that I have a negative 2y dy, which is du, and then I have the square root of u. So this is negative 1/2 times the integral of negative 2 to 2, the integral from negative 2 to 2 of the square root of u du. Well, of course, the square root of u, of the integral of the square root of u is 2/3 2/3 times u to the 3/2 power. So when we do this integration, we have 2/3 times u, oops, and that's a negative 1/2, my bad, negative 1/2. 2/3 times u to the 3/2 power, and then, of course, we're evaluating from negative 2 to positive 2. But, of course, u is 4 minus y squared. I'm running out of space, aren't I? So we have this negative 1/2 times 2/3 times, 4 minus y squared, and all of that's evaluated from negative 2 to 2. Looks like I'm going to need to go to the next page, so as we move to the next page, let me pause for just a second. Oops, I got ahead of us. I factored out the 2/3, so I have a negative 1/2 times 2/3, which is negative 1/3. Makes it a little simpler to deal with. And now we do our evaluation. I'm going to go across because I want the space at the bottom. So this is a little abnormal for the way I do things, as you know. So first we're going to evaluate it too. Oh, well, look at this. We're going to actually have 4 minus 2 squared. That's 0, isn't it? And then we're going to subtract from that 4 minus a negative 2 squared. Oh, all of that actually gives us 0. Well, that's nice. So what we have then, remember we said that we had our force that we're working on is 128 times the two integrals. That's the difference of those two integrals. And so we had the integral from negative 2 to 2 of 8 times the square root of 4 minus y squared dy, minus the integral that we just calculated, and we discovered that that value was 0. So all we have to worry about is this one single integral. So our fluid force is, well, look, we can factor out that that 8. So we actually have 128 times 8, which is 1,024. So this simplifies to 1,024, pardon me, times the integral of just negative 2 to 2, the square root of 4 minus y squared dy. Oh my goodness. Well, this still is a problem because we don't know how to integrate anything that looks like that. Now, in the next chapter, we'll actually learn how to do this. But we're going to use a geometric interpretation. Because remember what this square root of 4 minus y squared is. See, let's stop and think about that. This 4 minus y squared, okay, here's negative 2 for y, and here's, positive 2, pardon me, and here's negative 2 for y, and we had this circle, okay, like this, and the square root of 4 minus y squared represented the x that was right here, okay, this distance right there, okay, so with a dy and this value, that value is the square root of 4 minus y squared. Well, what are we doing? We're actually finding an area here, aren't we? And now this is an unusual observation. It's not something that we might normally observe. But we're finding the area. When we get all of this done, we're going to find the area, when we just look at that integral, the area of that semicircle. Well, the area of that semicircle, the area of that semicircle is going to be 1/2 the area of the whole circle. And how do we calculate the area of the whole circle? Well, pi r squared. But in this case, r is 2. So the area of that semicircle is simply 1/2 times pi times 4, which is, of course, 2 pi. So the conclusion we make from that is the integral from -2 to 2 of the square root of 4 minus y squared could have been interpreted in this case, only that part, as the area of that semicircle, which we know is 2 pi, by using a different calculation. We didn't actually determine the value of that integral by doing an integral. We recognized and interpreted what result it would give us. So the force in this case, F, is 1,024 times that integral, which we know has a value of 2 pi. Well, when we approximate pi, and we do this calculation, then we would get 6,434 pounds of force on that window. With a little strange twist, of course, for this particular problem. Well, that concludes what I have to say now about fluid pressure. I hope this is helpful as you do your homework. Good luck to you.